Okay, we finished the last video by looking at this graph right here, the square root of x minus 1. We found the critical number, plugged it in, got the critical point. We understand the function is undefined when x is to the left of 1, so we don't have to worry about any of that. If I plugged in something to the right, like 2, I get 1 over 2, 1/2, so it's positive. First derivative test tells me then, okay, the function is increasing. So does the graph look like that? And the problem is, we know from 171, the graph of that square root doesn't look like that. It actually looks like that. And now we start to have a problem because, well, if I'm graphing polynomials, we know they're nice and smooth. We did a parabola, we did a cubic, and they're nice and smooth and easy to draw. But what happens if it's not a parabola? The shape of the graph is different. The first derivative test just tells me if it's increasing or decreasing, but it doesn't tell me if it's increasing like a polynomial like this, or if it's increasing like this, which is different. And in order to find the shape, the curvature of the graph better, we actually need another idea. And there's a trick here. We'll come back to this. I'll leave it right up there. F of x equals the square root of x minus 1. But we're going to go back to what we've already done before. F of x equals x squared. We know we can do the first derivative test on it. Derivative is 2x. Critical number is 0. Critical point is 0, 0. Function decreases on the left of 0, increases on the right. So by the first derivative test, it's a minimum. Yeah. But now I'm left with the thought, if I didn't know it was a parabola, if I just know it's decreasing, since I know it's a parabola, I automatically do that. Why didn't I do this? Or something like that? That's also decreasing and then increasing. How do we know that the shape should be like that? And what we can do is, we can use the second derivative. Keep in mind, the first derivative is the rate of change of the function, so it's telling me where it's increasing and decreasing. The second derivative is the rate of change of the rate of change. In real-world applications, the common one we think of, don't jump up here, cat, is position, velocity, and then the rate of change of the velocity. Here she comes. There we go. The rate of change of the velocity, which is the acceleration. It's how fast the rate of change is changing. And if we can get an idea of what's going on with that, it will actually help me figure out the curvature of my graph. And the idea is the second derivative of 2x is just 2 right there. That second derivative is always positive. What does that mean? It means that that is always increasing. The first derivative is always increasing. If the first derivative is always increasing, well then either the first derivative is going positive to negative or negative to positive. If the first derivative is going from positive to negative, just make up some derivatives in your head. Suppose as you read left to right, the first derivative was going from positive to negative. So the first derivative was maybe 2, then 1, then 0, then negative 1. Those derivatives go from positive to negative, but that function is clearly not increasing because they're going down, which is impossible because the second derivative is positive. If the derivatives go from negative to positive, say negative 2, negative 1, 0, 1, 2, and so on, these derivatives are increasing, going from negative to positive. Since they're increasing, it means their derivative is positive, which is what we get here. I will put out here, this idea right here, when I was a student, always confused me. The first derivative test is straightforward and simple, and it uses ideas from pre-calc. This one always confused me. it takes a little bit of time to think about, so maybe pause the video, stop, and ponder it. If the second derivative is positive, it means my derivatives are going from negative to positive because they have to be increasing. Which means well, let's see. If I go back to my graph before we formalize it, we know the point is 0, 0. Out of the two possibilities, say in red we'll do this, and in black we'll do that. Out of those two, which ones make sense? Well, if you think about it, in red, keep things color-coded, the derivative right here is rather steep. Maybe it's like negative 10. The derivative here isn't as steep. Maybe it's negative 8. The derivative here is getting more horizontal. It's like negative 2. They're getting less negative, which means they're increasing. If we look at this one, the black one, here the derivative is really horizontal. So that derivative is maybe negative 2. Here the derivative gets steeper. It's like negative 10. And now these derivatives are decreasing, which doesn't work. Because the derivatives have to be positive, they have to, by positive, that means they have to be increasing, which means this isn't a possibility. So the graph has to look like this. And now I get an idea. Once I find my critical numbers, once I plot the critical points, once I do a sign chart, if I want to know the curvature of the graph, I look at the second derivative. As far as it goes, there's an idea here that for the curvature that does get mentioned in 171. I know because I mentioned it in my class. It's not a really big deal, but it usually comes up. And there's an idea of what's called concavity. Essentially, we don't need an incredibly complex definition here because it's graphical. Something can be concave up or it can be concave down. And the definition, easiest way to think about it, you're concave up if you hold water. And by holding water, that's actually how it was defined in math for me, it means you look like that, like a parabola. Because if I dumped water in this graph, it would sit right there and the graph would hold water. Concave down means you're a cup that's upside down. Because if I dump water on it, the water runs off the edges because the cup is upside down and it doesn't hold water. Now it looks like if the second derivative is positive, my graph looks like this. It's concave up. Logically, then, we would assume if my graph looks like that, which is concave down, then the second derivative should be negative. So test it. We'll actually do the easiest one I can think of. Negative x squared. All of you know that's a parabola that's flipped, which is clearly concave down. So do the derivative. Now do the second derivative. That's always negative. According to our logic, that means the derivatives start positive, get less positive, then they start getting negative, then they get more negative, which means the graph should look like that, curvature-wise, which is concave down. So the idea seems to work. What that means is, now if I want to graph things, I can use the idea of the first derivative and the second derivative. Just going back to this one. We did the first derivative. Let's see, it was 1 over 2 times the square root of x minus 1. Do the second derivative. Well, let's see. The 1/2 is going to carry along, and then that is x minus 1 to the negative 1/2. So here, if I want the second derivative, the 1/2 carries along. Chain rule. Bring down the negative 1/2. The inside stays the same. lower the power by 1, negative 1/2 minus 1 is negative 3/2, times the derivative of the inside, which is 1. And if I write it all out, there's a negative. 2 times 2 is 4. Negative exponent means it's x minus 1 to the 3/2 on the bottom. Now, because I care about where it's positive, where the second derivative is positive and negative, I do a sign chart again. I know the only point I care about is x equal to 1. There's still no zeros. And for this one, I know it's undefined over here, so I don't even have to worry about that. Now, pick a point over here. We'll just go with 2. If I plug in 2, 2 minus 1 is 1. The 1 to the 3/2 is 1. So it's negative 1/4 times 1, which is negative 1/4, which is negative. And on the last one, we said what? If the second derivative is negative, it means the graph is concave down. So now, I know if I want to graph it, we found my critical point, which was 1, 0. We'll say it's right here. We're undefined to the left. Don't worry about it. To the right, it's got to be increasing. We already did that with the first derivative test. It's always increasing, but it's concave down, which means, oh, it can't look like that because that's concave up. It has to be concave down, where it's always increasing, but the derivatives are decreasing. Here they're really positive, here they're less positive. And now we see where the graph of the square root comes from. This idea of the first derivative and the second derivative. Just like I did with the first derivative test, I'm going to formalize the test in the next video, and then we'll go through a bunch of examples. But I'm going to stop this one here a little bit short because we don't have enough time to write out the formal test. And because I think this is probably enough for your brains right now. And then, like I said, I'll make more videos with the formal test and with a bunch of examples of this graphing.